thank you everyone for joining the talk, and thank you also for taking the time to answer this question. I'm finding it like very interesting to see the variety in the responses. So let me read this question out loud for you. It says that I flipped a slightly bent coin 3 times, and 3 times it landed heads, and I will not flip it 200 times. So what's your best guess for the number of times that it will land heads? And part of the reason why there's so much diversity in the answers here is precisely because there's no right answer really. It will depend on what each of you understands by a slightly bent coin, whatever that means. But my intention here is really not to get a precise answer, but just to start provoking a train of thought that will lead us quite nicely into today's topic. Let's see what people mostly voted. Okay, so it looks like most people said option A, and between 160 and 200. So like a very biased coin. Yeah, it's very interesting. We'll come back to this example in a bit. So today's talk is going to be about Bayesian inference, and this is going to be a very introductory talk, not much prerequisite really, but it is nonetheless a technical talk, and it is aimed at data scientists. But of course, if you're not a data scientist, you're more than welcome to stay and listen, and also know that you're just as entitled to ask questions if you have any. Before I get into the actual talk, actually, let me introduce myself a bit more formally. I'm a data scientist at faculty. I came to the UK initially to study physics. I came to do my master's and my PhD. I did theoretical physics. And when I finished my PhD, I did faculty fellowship number 12. That was at the end of 2018. And the January after that, I joined faculty as a data scientist, and I've been there since then. In case you don't know us, if you haven't heard of faculty before, we are an artificial intelligence company. We are based in London, and our goal is to make artificial intelligence real. This means that we not only do a lot of research on the topic, but we are trying like really hard to make this technology accessible to you so that it can impact your business in a positive way. And we are, as a company, are quite young, really. We've only been around for 5 years, but we have worked with quite a lot of clients and across multiple sectors. So if you're interested in learning how AI can transform your business, definitely reach out to us. We'll be more than happy to talk to you. Okay, so enough of introductions. Let's now get into the actual talk. And here's the intended outline. I'm going to start with a very brief introduction to what the Bayesian workflow is. And this will be useful to set up our conventions, notations, and the language in general. And then we will see how the Bayesian workflow is relevant in machine learning. I'm going to do this with a very basic example that involves a logistic regression model, but we're going to put a bit of a twist on it. And having done that, we'll have a better understanding of why Bayesian inference is difficult, and then Stan will come in and save the day. So we'll also have some time towards the end to answer your questions. So please write your questions off the chat if you have any, and we'll come back to those at the end of the talk. All right, so in the Bayesian workflow, the first thing that we have to do is identify all the unknowns in our problem. So for example, in the quiz at the beginning, we don't know how bent the coin actually is, right? In a more realistic problem, there will be many things that we don't know, not just one, but it doesn't matter. We're going to put all of them in the same bucket. And that bucket is what we call the parameters. And since we're doing Bayesian statistics, we're going to express whatever little knowledge we might have about W, about the parameters, with a probability distribution. And that probability distribution is what we call a prior distribution. This prior distribution has more mass around the values which we think are more likely to be true, and less mass around the values which we consider less likely to be true. So for example, in the case of the bias coin, your prior distribution would have more mass around your initial guess, And how tight that distribution is depends on how confident you are about that guess. The next step in the Bayesian workflow is to specify a likelihood. And what is a likelihood? This is just a probability distribution over the data, but it's a function that depends on the parameters. In the bias coin example, the likelihood is really very simple, so we don't need to even write it down. The bias of the coin will be reflected in how often the coin lands at heads. And the goal of this likelihood function is to tell us how the parameters relate to the data. So for example, if the bias of the coin were 0.2, I would expect that 3 heads in a row would be a fairly rare event, so the likelihood is low in that case. If the bias was 0.4, 3 heads in a row would still be unlikely, but a little bit more likely than with the bias of 0.2, and so on. I can do this for all values for all possible values of the bias, all the way up to 1, in which case 3 heads in a row will have a probability of 1 because it will be the only possible event. But crucially here, the likelihood function does not completely determine what we know, right? The role of the likelihood is to update our prior knowledge. So applying Bayes' theorem to these two quantities, we get what is known as a posterior distribution. This posterior distribution represents our state of knowledge after we have seen the data. And not only we care about where the mean of this distribution is, we also care about the variance of this distribution. That is, we not only care what we know, we also care about how well we know it. So to illustrate Bayes' theorem in action, let me do a little demo for you. Here on the screen, we have 2 different individuals that start with a different prior for this coin flipping example. On the left, we have a uniform prior distribution, so someone who doesn't know anything about the bias of the coin other than it is a number between 0 and 1. And on the right-hand side, we actually have what was my prior distribution. I did a very careful piece of physics and on a napkin, and I concluded that this coin is it was going to be very biased towards tails, so that I predicted that it was going to come up heads only 20% of the time. So I put almost all of the mass around 0.20 and very little mass away from this value. But I was not super careful in my calculation, so I put some mass away from that value. It's not really that noticeable, but this function is not really 0 here on the tails. All I'm saying is that I think this coin is biased towards tails, and it will take a lot of data to convince me otherwise. So then I started flipping the coin, and the first thing I saw was a heads. And both distributions get updated immediately. Now on the left, what used to be anything is possible, now we think that it's more likely that there is a bias towards heads. But the important thing here, in my opinion, is that there is now a 0 probability that this coin will end up always tails, which of course, right, we just saw one flip that did not land tails. So we can say one thing for sure, this coin does not always come up tails. And what happened to the prior on the right? Almost nothing, right? Even though this outcome goes against my initial assumption, it doesn't quite prove me wrong, because at the end of the day, it's just one data point. So far, I'm going to stand by my choice pretty much. Then I flip it 2 more times. And okay, so now the student on the left is saying, this starts to look more and more like a coin that it will always land up heads. And on the right, I'm starting to think that I might have made a mistake. So this distribution has shifted slightly towards the right, but not too much, not too much. I then flip it a few more times. Okay, so what are we seeing now? The student on the left, it's thinking that this starts to look something like a fair coin, but we are not quite sure yet. So it's almost centered at 0.5, but it's quite a fat distribution, right? So we cannot make a solid conclusion yet. And me on the right, I'm still saying that there's not enough data to change my mind yet. So I'm almost at the same place where I started. So now I'm going to play the whole movie now, and you're going to see me flipping the coin about 200 times. And you will see that indeed this coin is biased, but I want you to pay special attention to how much data it takes for the student on the left to be convinced about it, and compare that to my knowledge on the right, on the right hand side. Okay, so here it goes. Okay, that was it. Interesting, right? There are a couple of things that caught my attention when I first did this. And first of all, it looks like initially I made a sign mistake somewhere because my prior was completely wrong. I was totally on the opposite side of the correct answer. And the only thing that saved me here is that I have left some mass of this distribution in the tails. And that means that it took quite some data to put me back on the right track, but it eventually did. And the other thing that you can see here is that both distributions, even though they started with different priors, they now both agree in that the coin is biased towards the heads. Actually, if you pay very close attention, you will notice that the distributions are not quite identical, but that's fine. There is sufficient overlap in the two distributions that we do not consider these outcomes to be inconsistent with each other. So what we were seeing now is Bayes' theorem in action. We start with an initial prior distribution that reflects the knowledge we have about the world, and then we gather some data. And with each new data point, we update our prior distribution. Before we move on to the next section, I would like to emphasize that quantifying uncertainty is not a luxury that is only relevant for a small subset of problems. I would argue that in real life, results that do not quote their error bars are borderline useless, right? To give a very extreme example, say there's an accident around Bermondsey and we are trying to get to the hospital and we would like to do that in less than 30 minutes. So if I take out my routing algorithm and look at the times, it would be immediately obvious that I want to take route A that takes 25 minutes. So 2 minutes less than the other option. But if I look at the full distribution of possible outcomes, I notice that route A could take anything from 14 to 35 minutes, whereas route B could take something from 14 to 30 minutes. And now route B starts to feel more and more like the better option, right? So having a good quantification of uncertainty, it's very important in real life applications. And another comment that I would like to make here is that the Bayesian framework will feel very natural for quantifying uncertainty in problems, but it is certainly not the only way. And for many years, a breed of statisticians that go by the name of frequentists have been quantifying uncertainty in different ways. They may point fingers at you if you start placing probability distributions over parameters in the first place. But I will have to emphasize that while there are differences in the formulation of these approaches, they are both mathematically correct. They are just different. And here I'm not interested in seeing, in comparing these two approaches to see which one is better or anything like that. I'm just interested in how the Bayesian framework can be useful, and particularly how it can be useful in machine learning. And that brings me to the next section, which is the topic of learning as inference. So the Bayesian framework will make two important differences in the way we do inference. The first one relates to the way we fit our models. In the traditional approach, we use regularization to prevent the parameters from blowing up, and this way we prevent overfitting. But in the Bayesian framework, we are going to use domain knowledge to set a prior distribution over the parameters. The next important difference is about the way we make predictions. Usually we do so by simply using the best fit parameters. But in the Bayesian approach, we are going to actually use all possible parameters that are consistent with the data. Yes, some parameters will be better than others, but we won't worry too much about that. We still want to use them all. Now, this might sound very confusing right now and a lot of words that do not make a lot of sense. So do not try too hard to make sense of this slide. The point of the talk is precisely to do that. But I'm going to make things a little bit less abstract, I'm going to use a toy example for this. So say you're given this lovely binary classification task. So your labels are only zeros or ones. And your client has asked you to do classification on this data set, and you decide to solve your client needs by using a logistic regression model. Just as a reminder, in a logistic regression, we assume that our labels follow a Bernoulli distribution, like it has to be for any binary variable, really. But importantly, the parameter of that Bernoulli distribution is given by the inverse logit function of that product of x times w. And this inverse logit function is also known as the sigmoid or a logistic function, however you want to call it. Usually, though, we don't have to worry about all that. All we have to do is import logistic regression from your favorite library and fit the model. And here intentionally, I have decided not to use regularization, and that when I make predictions over each point in this 2x2 square will give me a decision boundary that looks more or less like this. And now I would like to have your opinion again. So I'm going to go back to the quiz page and have another question for you so that you can participate as well. And the question is, I'm now going to fit a logistic regression model on these points, but I'm going to do so with regularization. So when I don't put any arguments on this class, sklearn will default to have some regularization. So the question is, which of these images you think will be the classification boundary? I'm not expecting you to do any maths here. I would just like you to try your best guess, really. Whatever you think makes sense. And let's just give a few minutes for you to answer. This QR code here again. It's very close. Oh, wow, okay. Are we going to have a clear winner? I'm going to just, okay, I'm going to finish there and reveal what was the winner. Okay, so most people think that would be the center image, and indeed, that is the right answer. When I do regularization, the classification boundary turns out to be something like the center image that we just had. But in my opinion, the other two options that we have feel also almost just as good as this one. And it is not immediately obvious to me that this is a much better classification boundary. And I'll come back to this topic, but for comparison, here is what you would get without regularization. And we all know what overfitting is. So I'm willing to say that we can all agree that the result on the right feels better. If we don't regularize, the classification boundary is way too tight, and we are not willing to believe such a sharp division of the data, especially with such a low amount of data. The classification boundary on the right feels less extreme, feels closer to our intuition. But something important here is that the other two options that we had, which also are quite intuitive in my opinion, the three options disagree on what the prediction should be for the points that are far away from the data. They all agree in the region where we have data, so that's good. But how this boundary should extrapolate away from the data, that's where we had a difference. But importantly, they all had this same weird behavior where the boundary extrapolates in a straight line far away from the data, as if I had data here. And I feel like this should bother you a little bit, that the boundary is just as tight in the region where we have data and in the region where we don't. To understand how we're going to fix that, we're going to need a bit of a change of perspective about how we fit our models in the first place. The traditional point of view is the following. When we are fitting a model, we are trying to minimize a cost function, right? Generally, that cost function can be written as the sum of two terms. First, we have an error term that depends on both the parameters and on the data that we are trying to describe. And the second term is what we call the regularizer. And crucially, it only depends on the parameters. There is no data dependence on this term. Now, fitting the model means that I'm trying to find the set of parameters that minimize that cost function. By the way, for simplicity, I've excluded some dependence on the features x, just to declutter the notation and to keep the discussion simple. If you had x in these functions, there are some other assumptions that you have to make, and you have to be a little bit more careful, but the message still follows through. So I've just excluded it here to keep the discussion simple. Okay, so now comes the change of perspective. I'm going to take that cost function, put a minus sign on it, so that now I'm flipping it over, and then take the exponential of that number. So now everything is a positive number. And now, whether you like it or not, I'm going to say that this quantity is my posterior probability distribution. That is, I'm going to say that this quantity here represents my knowledge about the parameters after I have seen the data. Now, an obvious issue here is that probabilities should integrate to 1 in the first place. And I have nothing on the right-hand side that guarantees that this will happen. So to fix that, I can just divide the whole thing by a suitable normalization factor. So what we have now is that what used to be the minimum of our cost function now becomes the highest point in this posterior distribution. That highest point is also known as the mode of the distribution. Now remember that because of Bayes' rule, this posterior distribution can be actually written as a product of two terms, the likelihood and the prior. And for the cost function on the right-hand side, what used to be a sum of two terms now, because of this exponential that I have, it also becomes a product of two terms. And I have this very nice correspondence in which, from the Bayesian viewpoint, the error term corresponds to the likelihood and the regularizer corresponds to the prior. And this can be seen as a simple reinterpretation of things, yeah. But I think that this interpretation is actually very powerful. First of all, a prior is more than just a regularizer, right? A prior is something that encodes information about some information we have about the values of the parameters. And that can be a lot more general than just saying the parameters will be close to 0. But perhaps a more interesting aspect of this reinterpretation is when it comes to making predictions about unseen data. So in terms of mathematics, making predictions is a very precise question. The question is, given the data so far, what should my probability distribution be over the new data? And here the new data, I denoted it with y tilde here, just to distinguish it from the data that I've seen so far. And it's nothing very difficult to show that that integral can be written as the integral on the right-hand side. But the point here is that this integral has a very nice interpretation actually. If you stir it for long enough, you'll notice that this integral is just the average of the likelihood function under the posterior distribution. Now, despite this seemingly simple answer, integrals are integrals. No one solves integrals exactly, and we're not going to do that either. We're just going to try to use approximations for this integral. And in the traditional approach, the way you approximate this integral is that you put your hands in the air and said, this is way too difficult. So instead of solving the integral, I would just assume that the whole contribution to the integral comes from a single point in parameter space, which means that I'm just going to evaluate the log likelihood at a single point, at which point that will be the mode of the distribution. Now, perhaps needless to say, this is a terrible approximation by any means. On the Bayesian approach, though, we're also going to make an approximation, but we're going to try a bit harder. And a way of doing this approximation would be that since what we are trying to compute is the average of something, I can compute average by taking many samples. So I take many samples of W from the posterior, I plug them into the likelihood, and then I take the average of that. So I approximate that integral by taking the sample average. So the problem here is that I have just traded one difficult problem for another, which is how am I going to sample from the posterior distribution? Remember, this posterior distribution is something that depends on the data that you have. So generally, it will be something very complicated. Suppose, for example, that your posterior distribution ends up looking something like the banana-shaped distribution right here. If this was a normal distribution, I could just use numpy.random.normal and generate samples, but there is nothing, or there's not yet a numpy.random.banana that can generate samples from this distribution. So how do we sample from this? This is precisely the problem that Monte Carlo methods solve. The Metropolis algorithm is one of the many versions that exist of this algorithm, and many PhD students and researchers have dedicated their sweat and tears to the details of this algorithm. There are books and songs written about it. So of course, I will not go into the details of how it works, but in essence, what's happening is that you send a tiny explorer to do a sort of a clever random walk around the target space. And then this explorer will collect or reject samples according to a well-defined mathematical rule. The idea here is that if you let this explorer walk around for enough time, then the points that are collected will be a good approximation for your target distribution. Nowadays, there are better, more efficient methods, more efficient versions of the Monte Carlo algorithm, but they are quite difficult to code yourself. So we're not going to do that. Instead, that's where Stan comes into play. So Stan is a probabilistic programming language, and the way it works is that you specify your prior, you specify your likelihood, and Stan will give you Monte Carlo samples of the posterior distribution, just like that, really. How does it actually work in practice? Well, you have to write a file, a separate file, a .stan file, which would look something more or less like this. And let's break it down. The first thing that we note is that the Stan program is defined in blocks. Here we have the data, parameters, and model block. And really, this is something very natural when defining a probability model. You have the data, the things that you know. You have the parameters, what you don't know, and you have your model, how those two things interact with each other. There are other blocks in Stan, but these are the most basic ones, and really to get started, that's all you need. The other thing that you note is that Stan is a statically typed language, which means that you need to declare the type of each variable, and that type cannot be changed later on. Stan has many built-in types that are familiar to us, like integers, for example, but it has also many other types that are useful for specifying probability models. Here is, for instance, an integer type with a lower bound of 0. And we also have a matrix type, which is more than just an array, right? A matrix has more properties than just a simple array of numbers. It has vectors as column, and it has a specific multiplication rules. And there are many, many more types. The amount of types that are available in Stan is actually quite impressive. And it's one of the great features of the language because it makes your life a lot easier when writing models. And note that while I'm declaring the data that I'm going to use, I haven't actually instantiated any values, right? I am not saying that n has to be equal to 10 or anything like that. I'm just telling Stan what are the data variables that I'm going to use, but I'm not actually passing the data. That will come later when I interface it with Python. The next thing we have is the parameters block. And here's where we declare all the variables that we don't know and those variables for which we want samples. And I'm doing a logistic regression in 2 dimensions, so I just need 2 parameters. Well, I'm ignoring the intercept on purpose. And for convenience, I've bundled these 2 parameters into a vector. I could have written them as just as an array of numbers, but it'll be useful for me to have them as a vector. And finally, we have the model block. And in the model, like I said before, we specify our prior and we specify our likelihood. Here I'm telling Stan that W has a standard normal prior, which is equivalent to an L2 penalty, and that's actually the default regularizer in sklearn. And then there's the likelihood, which is telling Stan that Y is distributed according to a Bernoulli distribution, and the parameter of that Bernoulli is the logistic function applied to the product of X and W. This is just logistic regression. A cool thing here actually is that the Bernoulli distribution and the inverse logit function are actually quite compatible. So we can gain some numerical stability by taking advantage of it. And Stan has this built-in distribution called the Bernoulli logit, which is mathematically equivalent to what we had before, but this is a numerically stable implementation. Okay, so once we have written our Stan file, we go to Python and read the model using the PyStan module. We instantiate the model using the Stan model class. We just have to pass the path to where our file lives. We bundle our data into a dictionary, and to generate samples, we use this .sampling method with the data as an argument. If you want to visualize the samples, you could use something like this joint plot of Seaborn to make a KDE plot. It will look something like this. So you get access to the full distribution of the parameters. So now let me actually go to a Jupyter notebook that I have here to show you how it actually looks like in practice. In my local file tree here, I have my model.stan file, which is the file I was just showing you on the slides. And here in the Jupyter notebook, I have instantiated my model using the Stan model class. I have some setup here on the top, which is the boring aspect, the imports, some function definitions that I had to do myself, but that's the boring stuff. That's also where I have the data. But here's the important bit. And you will see this compiling the C++ code message. This is because Stan actually runs, compiles to C++, so it's actually very fast. But that means that you have to wait a minute or 2 for this model to compile. And just for the sake of saving some time, I have skipped that compilation step. I've done it ahead of time so that you don't have to wait for it. If I then print the model code attribute, you will see the code that reproduces the same content as the file that you had. I put the data into a dictionary here. And crucially, an important aspect is that this dictionary, the keys of this dictionary correspond to the variables that I have declared in the data block, right? They have the same naming convention. Then to sample, I do model.sampling with the data as an argument, and the samples would look something like this. This is the object representation that the Stan developers have chosen for Stan, and we normally read it. Well, I normally read it like this. So I look for the parameters that I'm interested in, which is W's in this case, and the first column tells me the mean estimate of those parameters. Then I skip this column. I don't think I ever use that. And then I go straight to the standard deviation to get a feeling for how uncertain the values of those parameters are. And there are other quantiles here that might be useful for you. And the other important columns that we have are the last two columns, which is here NF is the effective sample size. So the samples that we get using Stan are actually correlated samples. They do not have the same power as independent samples. So notice that Stan actually drew 4,000 samples, but that is equivalent to just having roughly 1,300 samples. But that's fine. So if you are worried about the precision that you want to get on your estimates, this is the number that you should be looking at. And finally, we have the R hat column. So this is a slightly complicated number, but the way to think about it, if you go back to that picture of the explorer that goes around collecting samples, well, normally you don't have just one explorer going around, you have more than one. And the idea here is that if the explorer do not agree on what they see, then R hat would be far away from one. And in those cases, you cannot trust your results. The actual values of the samples, you can get them as you would in a dictionary. So by calling the keys here. And here I see the many samples of my two-dimensional object. And I can do a joint plot like I did on the slides. And that's how it looked like. So now what I'm going to do is that I'm going to choose some samples from this distribution to make predictions on this 2x2 grid. And I'll show you how those predictions look like. So that's the mesh grid in which I'm going to make predictions. I take a random sample of all the samples that I have available. I do a logistic, I apply my logistic function with that sample over the mesh grid. And the classification boundary ends up looking something like that for this sample. But I could have chosen a different sample, right? What if I change that? Then I get something different. It's actually similar to one of the options that we had in the quiz. I could have taken another one. And maybe you see where I'm going with this. The point here is that you end up with many, many options to make predictions. Each sample that you have gives you a different classification boundary, and they mostly agree in where you have data, but they vary a lot as you move away from the data, right? And you have many, many options. It's not clear at all if you choose any of those. Here I'm just showing you how the predictions look like for many samples of them. And an important, well, one of these samples happens to be what you get using sklearn, but it's not obvious that I should choose one, right? That all the predictions make just as much sense as that one. So we are not going to use any of these predictions. Instead, what we do in the Bayesian inference workflow is that we combine all these predictions into a single one. And that's when things become interesting, and you see a very nice pattern emerging where the classification boundary starts to look a bit different as you move far away from the data. And this is only by taking the 20-something samples that I had on the screen just now. But if I take the 4,000 samples that Stan gave me, that pattern will become something like this. And what you're seeing right now is in fact the average prediction of many models, right? Of many values of the parameters. And I don't know about you, but when I first saw this, it blew my mind right away. Even though the math is rather straightforward, it's not a complicated piece of math. But the fact that we have this non-linear boundary out of a linear model, because it's still a linear model, right? I'm still doing logistic regression. but the boundary that I get is nonlinear, which is quite cool in my opinion. But something nice here as well is that the boundary is just half of the story. Now that I have access to the many predictions of my model, one thing I can do is, yes, compute the average like I just did, but I could also compute the standard deviation. And now we have this very powerful picture where basically I can see the regions in which I can trust my model and the regions in which I cannot trust the predictions of my model because there is so much variation in the predictions. So just to conclude and have some time for questions before, let me make some final comments about this. So we've seen that Bayesian modeling is quite a powerful way of incorporating domain knowledge into a model because you can encode that into the prior distribution. And Bayesian modeling is quite a natural framework for quantifying uncertainty. Another important aspect here is that Bayesian modeling is quite hard computationally and mathematically. The Stan will make your life easier in terms of the computational aspect of things, but even then, it will still be difficult. There's still a lot of mathematics that you need to learn. Just be familiar with all the statistics lingo that people use. It's not always very intuitive. It can be quite challenging. Another important point that should be mentioned is that Bayesian modeling is not always the right tool for the job, right? Especially because of these computational constraints, they can be quite a challenge. If your sampling here was fast, but in a real life model, sampling can take a lot of time depending on how much data you have or how complicated your model is. And that can be an obstacle. Another piece of advice that I would give you here is to stay away from the frequentist versus Bayesian debate. Remember that you are a scientist, and identifying as a Bayesian or as a frequentist will only hinder collaboration. It will hinder science. It will prevent you from taking advantage of all the tools that you have available. So just do what you have to do to get the job done and leave the debate to the internet community or other people. And if you want to learn more about this topic, I would highly recommend the textbooks by Andrew Gelman, really any textbook by him and his collaborators. And also there's a very nice blog by Mike Betancourt. Both of them are in the Stan developer team, and they have very nice resources. I've really learned a lot from them. Okay, finally, let's have some time to answer some of the questions here. One of the questions that I have here at the very beginning is, what are the limitations of Bayesian modeling? And well, in my opinion, one of the limitations is computation. It will take a lot, they take a lot of time to fit, especially as you gather more and more data. There are other options that are not based on Monte Carlo methods, but really Monte Carlo methods are the best ones. That's maybe open for debate, but Monte Carlo is the gold standard, and it's usually very slow. It scales with the data, like as you have more data, they get slower, and it sometimes it's just not an option to be waiting that more time. In real life, you need to iterate, you need to improve, you need to test, validate, make changes, and having that time barrier can be really problematic. But other challenge, in my opinion, is that when encoding prior knowledge into a model, we have to do it based on distributions that are not really familiar to us. Like you will have to say things that, oh, I think that this parameter follow a student T distribution or a Cauchy distribution or whatnot. And I don't know about you, but I was not familiar at all with those distributions, and that's not how I intuitively think about the real life parameters. So first you have to be able to translate your knowledge into a probability language, and this probability language was not precisely designed to encode your knowledge. So it can be quite a challenge here. Let's see. I have another question that says, did you apply the log to the numerator and denominator in the cost function and the prior posterior? I think that's referring to the way I interpret the cost function as the cost function as the posterior. And yes, so the idea is that your error term becomes your negative log likelihood, and the regularizer is the negative of the log prior, the negative log prior. So yes, you have to apply the logarithm to make the correspondence work. Would you be able to, I have another question here which says, would you be able to share with us the implementation of these steps? Yes, that's a good point. I wanted to make this available on GitHub, but I haven't done that yet. I'll make sure to do that after the talk, and maybe we'll send you. I'll send you the link on the email list. Does the mode give you a different answer to Monte Carlo samples? That's a very good question. So the mode, taking the mode sample, so the sample at the peak of the distribution, and making a prediction with that would be equivalent to using just doing the traditional method, almost the same thing. It will have the same issues in that you have this boundary that extends in that maybe does not generalize when you gather more data. But that answer that you get by using the mode will be different than the one you get when taking the average of many predictions. And notice, it's not the same as taking the average sample and then making predictions with that value. What you want to do in Bayesian statistics is make many predictions with different samples and then average the predictions. Do not average the samples and then make a prediction. And in general, yes, the results will be different. I have another question which says, how did you compute the standard deviation of the posterior? Can you please share the implementation of it? Okay, I think this was related to the question before. So I'll make sure to share this notebook with you so you can go through it in more detail if you want. I have another question here, which is, what about other frameworks, MCMC3, TensorFlow probability, that may be more scalable? That's a great point. So there are many probabilistic programming languages. Stan is a very popular one, but there are other options out there like PyMC3, TensorFlow probability, Edward. There are really way too many options, and each has their own advantages and disadvantages. One, for example, Stan is great for Markov chain Monte Carlo stuff, and whenever there's a cutting edge improvement to the Monte Carlo methods, it's most likely going to make its way to Stan first. However, when it comes to variational inference, Stan is just not good. I don't think, but I don't think it was designed for it. It's not even well documented, so they will actually probably remove it, or I don't know if they are trying to improve that aspect. But then you have Pyro, for instance, which is great for variational inference. So you have to explore your options. I just use a Stan because that's what I started with, and I like the community around Stan. They have a very nice forum where you can ask questions, and people are very active and very engaged on it. So you have a lot of support. Here I have another question. How do you decide when to use Bayesian modeling? Do you have any rules of thumb? Okay, I think my rule of thumb is that I would try to default to use Bayesian modeling. Maybe it's not always the right decision at the beginning, but I always end up learning something by trying to go Bayesian. And only when it proves to be impossible or very difficult, then I move on to other approaches. I'm saying that that's the best approach to doing things, but and that's the way I do them, because I find this Bayesian viewpoint to be very enlightening, very illuminating in many situations. And okay, I have another question here saying, what is the difference between Stan and say other Gibbs samplers such as JAX for R? So the Stan uses a Monte Carlo algorithm that is called a no U-turn sampler. It's based on a previous version of Monte Carlo called Hamiltonian Monte Carlo. And the way they work is, it's an algorithm that has some physics analogies working in the background, and they are very efficient. They are very fast. And this a Gibbs sampler can be slower. For many problems, the Gibbs sampler will just not converge. So Stan has this option of this adaptive Hamiltonian Monte Carlo algorithm, which is really like the latest in Markov chain Monte Carlo. But you can use Stan from within R. There's R Stan, and actually the R interface to Stan is much more mature than the one for Python. The developers of Stan are more active in R than they are in Python. So if you are an R user and you want to use Stan, that it's a great option in my opinion. Okay, I think we're running out of time, and there are a lot of questions. I'll try to answer these questions for you on the email separately. Thank you so much, everyone, for coming. By the way, if you want to get in touch, don't hesitate to send us an email. If you have other questions as well, send an email over, and I'll happily reply to those. So yeah, thank you very much for attending, and I'll see you next time.